So GIT2. And let me start first by giving you some references. So in this course, I will be mostly focusing on classical algebraic geometry, on varieties. And since I will be assuming now and then I'm dealing with a linearly reductive group, I will be assuming characteristic 0 a lot of times. So if you want to view something that works in all characteristics, you can go to the book of Newstead, which is Introduction to Moduli Problems and Orbit Spaces. Okay, it's a set of notes published by Tata. If you want to see the full thing, you should go to Mumford, GIT. And if you want to see the construction of the moduli of curves, I just hinted at the beginning of the first lecture. You can see this construction using the methods that we're going to give here in the notes by Gieseker, moduli of curves, in the same series where these notes of Newstead were published. Okay, so we're now going to consider actions and quotients. So we'll first be concentrating on the affine case, and then we're going to move to the projective case. But part of it is more general, if you want. So let G be an algebraic group defined over a field, algebraically closed. Okay, and X be a variety over the same field. Okay. By definition, an action of G on X is a map, a morphism, from the product to X, satisfying the following two conditions. First, the neutral element of the group must act trivially. Okay. Second, that the action must respect this property here. If you apply G2 and then apply G1 to the result, what you get is the same thing as applying the product. Okay, so this should hold for every G1 and G2 in G, and for every X in X. Okay, so that simply put is what an action is. We're going to use a shorter notation. We're going to just write the Gx for sigma G of X, right? And with this notation, things become a bit simpler. So the two properties are this one and this one here. You may regard it as some sort of associativity. Okay? So an action, sigma, induces a homomorphism of groups from G, and call this rho, from G to the linear transformations of the ring of regular functions. So these are functions that are regular. Okay. And it's simply giving as follows. So if you have an element, you have a linear transformation that acts on a function, giving another function which on X is simply given by applying G minus 1 to X and then evaluating by F. Okay? So it's basically the same thing we had before. This, in a sense, is homomorphism of algebraic groups, though I cannot talk really much about algebraic groups because this could be infinite dimensional. But locally it is. So there are two propositions that I'm going to talk about. First one is that if V is finitely dimensional and invariant, invariant under this action here by rho, then we have an induced action and this is a linear representation. That is, it's a homomorphism of algebraic groups. Okay? Now the proof of this is very easy, so let me do it here. So you just pick a basis of V, of functions, right? And so these are functions on X, and they are linearly independent. So as an exercise, you can show that there are points such that the matrix where you evaluate these functions on the xj's, this is invertible. Okay. I'll leave this as an exercise. It's just because these Fi are linearly independent. Okay. And then what you have, since this is invariant, you have that when you apply rho g to an element of the basis, you get a linear combination with scalars that depend on j. So these aij are functions from j to k, from g to k. Oh, by the way, I'm going to do it simply. I'm just going to assume everything reduced, okay? So that I'm not worrying about nilpotents here. Okay, so we have a function here. And to show that you have a linear representation that is not only a homomorphism of groups, but a morphism, you just have to show that these are regular functions. And you do that by evaluating on these guys here, on both sides. And observing that you have here a product of matrices, of these two matrices. So that since this matrix here is invertible, you can just write this matrix here as this one, which is simply given this way, times the inverse of this one. Okay? Now, these entries here depend regularly on G. They are regular functions. So are these. Okay? So these aij are regular. Okay? So for every finite dimensional invariant space, you have a linear representation. And more than that, in the affine case at least, proposition 2, if X is affine, right, and V is finitely dimensional, then we can consider V prime as the subspace generated by Fg, where F is in V and G is in G. Okay. Then you have a subspace, and this subspace is invariant, which is easy to see, and finitely dimensional, which is the real statement. Okay? So if you're interested in understanding the action of rho into some functions here, a finite number of them, you can work on a finite dimensional vector space. Just pick the space generated by the action of the group on these functions. Okay? So how do we show that? Well, it's clear that it's invariant. We have to show that it's finite dimensional. Bertrand did something very similar. I would just, last week, so I would just sort of put here the same argument again. So if we have, say, V is finite dimensional, so it's generated by a finite number of functions, right? And thus, this V prime is generated, since the action is linear, by these Fi's and their modifications. Oh, by the way, I forgot to put it here, but I'm using the notation of last time, where I put the action on the top. Okay, so this is just the notation I'm using here and here. Okay. So we have these functions here. We have G. So G can be decomposed, where these UIs are affine. Right? And then, if you want to view a bunch of these, I mean, what we do is something like this. We look at the action of these affines on X. So that's the action sigma, restricted to that UI times X. And then you apply Fj. Right? So you have a regular function there. And here you have a product of two affines. So that means that you can write Fij as the summation of Bijl, Cijl, where these Bijl are regular functions on UI, and the Cijl are regular functions on X. Okay? So that's the structure of, the regular functions on the product. And now what you see is that if G is such that the inverse belongs to, yes, because we're applying the inverse here, is such that the inverse belongs to UI, then Fj G belongs to the space generated by this Cijl for L running. Right? Because because Fg is given in this way. So if the G inverse is in UI, what we need just to apply this, and then we're going to have here some elements in K, and then a linear combination of the Cijl. Okay? So as you have to run through a finite number of these UIs, what you get is that the V prime is inside Cijl for I, J, and L running, whatever it has to run. Okay? So you get the finite dimensional there. All right. So now we have an interesting corollary, which is a variation of a theorem that Bertrand showed last week, which is the following, corollary 3. So let G be an algebraic group acting on an affine variety X. Then there are an integer, a linear representation, rho of G in GLM, and a closed embedding iota from X to AM, such that the action of G on X is induced by that on AM given by rho. Okay, so here we have a linear action on AM, right? You have a matrix, you multiply here, you view this as column vectors, right? And what I'm saying is that you can concoct everything here such that when you restrict this action to X, then what you get is the original action that you're given. Okay? If you apply this to an affine algebraic group acting on itself, then what you get is that, well, you have to work a bit, but what you get is that this affine algebraic group is a linear algebraic group. There is a group of matrices. So we're going to use this because last time in the first lecture we studied this action, right, of G on AM, linear actions, and we showed that the ring of invariants is finitely generated. So we want to show that the same thing holds for any action on an affine variety, and we're going to use this. Okay, so proof is again quite simple. So we look at the ring of regular functions on X, right? It's a finitely generated ring. So let me write here generators, F1 up to Fn. Right? Then we know that there is an invariant, finitely dimensional subspace V containing these functions. Okay, so that's proposition 2, right? And then, I mean, what we can do is look at, expand this to a set of generators of V. They will generate the algebra as well. So we may assume that this F1 up to Fn form a basis of V. Okay, so just by expanding the number of generators to form a basis. And so, since we have this, we have an embedding of X into AM given exactly by these functions. It's an embedding because they generate X, they generate the algebra. So we have here an embedding. And on the other hand, you have that the space V is invariant. So you can write Fig inverse as a linear combination of F1 up to Fn. So that's going to be summation of Aij G Fj. Right? Where these Aij, they are regular functions on G. So you have rho a representation, GLM, or N actually. This is N because I'm picking N functions, right? So that associate to G, Aij, G, this matrix. Okay? So from the properties of the action here, you see that you actually have a homomorphism of groups, and it's algebraic because these functions are regular. Right? So now you see that if you let rho of G, so this acts on AN, right? And if I act on iota of X, right? So what you get is iota of G of X, because, so this follows directly from applying here X, from evaluating at X. Because when we evaluate at X, what we get is Fi of Gx here, and on the other side, the multiplication. Right? So if iota of X is evaluating by the Fi's, right? Then apply rho G, that's what I have here, in a sense. Okay? And over here, I'm applying the Fi on Gx. Okay? So, and this tells me that the action, when we restrict to X, is the original action on X. Okay? So now, we're going to use this, as I said. First, the same notation as before, so notation. I'm going to look at kx of G. So these are the functions that are invariant. Okay. So this is a ring. It's the ring of invariants. And the theorem we want to show is that if G is a reductive algebraic group acting on an affine variety X, then the ring of invariants is a finite generated K algebra. Okay. So that's the statement. And then the proof. So we're going to use that corollary. So we may assume X is inside some affine space, and the action of G lifts to a linear action on AN. Okay, so that's exactly the corollary. Now, since the action is linear, and since G is reductive, from the theorem we stated last time, we know that the ring of invariants on AM is finite generated. Okay. So now what we do is we look at the restriction function. Right, so we have here a AM, or AM, I don't know. Switch back and forth. But here we have the ring of invariant functions. We have the restriction to X, right? Now, if we look at this map here, psi, then it's clear that the image of psi, so if you have a function that it's globally G invariant, then it's going to be also in the restriction. So that lives inside the ring of invariants of X. Okay. So now what we have to show is that we have equality. Right? Because if we have equality, the generators here will give me generators here as a K algebra. So let's show that. But just in the special case where G is linearly reductive. So I'm going to use some properties of linear reductive groups. So assume now G is linear reductive. So as I mentioned, I'm going to state everything for reductive groups, when it's valid, of course. But in the proofs, sometimes I'm going to assume that you have linear reductive. Okay? To simplify it. Okay, so what we have to do, we have to pick an element here, which is invariant. Of course, any function here is a function on X, so it's a restriction of a function on AN. Is always surjective. So let me pick a function here such that f restrict to X is invariant. Okay. If we look at I, the ideal of X inside this polynomial ring, right, so let me call I this, then this I is invariant. That is, Ig is equal to I for every G, because X is invariant. Right? And to say that this is invariant is the same thing as saying that when I apply G, I get something that's congruent to F mod I. Okay. Now what we have to show is that there is something invariant above, a polynomial which is invariant, right, such that H is congruent to F mod I. Okay? So an invariant function here such that when you restrict mod X to X, that is mod I have F. Okay? My original invariant function. Okay, so just take, to start with, any X. Why not F, right? Yeah. Just a moment. We have F itself. Yeah, why not? Okay, so what we do is the following. We consider the subspace generated by this Fg, by Fg, inside K of AN. So it's finitely generated, it's finite dimensional and invariant. Right? And the map from V to the quotient, right, which is this guy here, surjects onto K F bar. Okay? Because of this, Fg is congruent to F mod I. Right? So it's the same class. Okay? Then we do as before. We consider the linear functional such that f psi of V F bar is equal to V bar. Okay, so V is a function. I can restrict it mod I, right? And everything here is a multiple of F bar, so I'm denoting by this psi this multiple, and this psi is invariant. So what we have to show is that psi g applied to V, right? Which is by definition psi of G inverse applied here. So that's V G inverse, because that's the action, right, on functions. I'm denoting this way with G on top, right? So what we have to show is that this guy here is equal to psi of V. Okay? So the psi of G is equal to psi. Okay? So this is something I didn't do last time, but let me do it here. It's a similar argument from last time, just to show you how it's done, but it's very easy because you can write V since it's inside here. So you can write this as the summation of Ci Gi, where the Ci's are in K. Okay, so it's a generated, V is generated by these guys. So you have this, right? And if you apply G inverse, what you get is this Gi G inverse, and that is the same thing as F G inverse Gi. And when you take the bar, you're going to see that this is the same thing as V G inverse bar, okay? Because when you apply bar, it doesn't matter what you raise here, you get F back. So everything is the summation of is simply this. Okay? Right? It's the same class. Right? So then psi is invariant, and then since G is linearly reductive, there is an element in the dual space, there is a V, which is invariant, such that psi of V is non-zero, and we can take it to be equal to 1. Okay? So this V is actually a function. Which is invariant, because it's an invariant function there. And we have that since psi is equal to 1, its class is the same as the class of F. Okay? And that finished this. We found a function, V, invariant, whose, mod I is the same thing as F. Okay? So that's the argument. And that finishes the proof of the theorem, so that you get a finite generated K algebra. Okay. Now, what can we do with that? Well, it's very tempting, since it's a finite generated K algebra. So if you have now a G a reductive group, acting on X an affine variety. Right? So it's very tempting to consider the affine variety Y such that the ring of functions is this finally generated K algebra. Okay. And since we have an embedding, we have a map. From X to Y. So the question is that, so what is this Y here? Is it a quotient in some sense? Right? So we're going to see that it's actually a quotient, and a good quotient by definition of good quotient. So what's a quotient? We may consider the notion in the categorical sense. So definition. It's more general, and we're going to need it. So let G be an algebraic group acting on a variety X. Then we say that a quotient, and that's the categorical notion of a quotient of X by G is a morphism pi from X to Y, such that the following two conditions hold. First of all, it must send an orbit to a point. That is, if I apply G to X, then I get back the same thing as just with X. And second, it must be minimal with this property. So if there is another morphism with the same property, such that psi G of X is equal to psi of X for all G in G and X in X, then there must exist and be unique a morphism from phi from Y to Z, such that psi is the composition. Okay? So in terms of diagrams, what we have is the following. It's unique. It's unique by by the property. Oh, I mean the quotient. The quotient is unique up to unique isomorphism.
Not the map.
The map is unique by definition. Yeah, we require it to be unique, and from that uniqueness you get the uniqueness up to isomorphism of the quotient. Yes. Okay, so in diagram terms, we have the action here. Right? Here we have the projection. So here we make gx, here we just take x. And what we need, the first condition, is simply that this diagram must commute. So that's condition 1. And condition 2 says that, condition 1 is y. Right? So that's the first condition. And condition 2 says simply that if we have the same thing for another map, okay, so if this diagram here commutes, then we must have a map here, and a unique one, such that this triangle commutes. Okay, and of course this one as well. Okay. So that's the categorical notion. And then I'm going to pass to here because I want to leave some stuff on the board. I'll pass to here. Then what we're going to see is that what I just erased is actually a quotient. But even stronger than that. So theorem 5. So let G be a reductive group acting on an affine variety X. So let Y be the affine variety such that K of Y is equal to K of X, G, the ring of invariants, right, and pi, the induced map. Okay, given by the inclusion, as I mentioned before. Right. Then, pi is a quotient of X by G. But not only that, it comes with many interesting properties that allow us to actually study this quotient. Second, the map pi is surjective, something that is not required for a quotient. 3, if z inside of x is closed and invariant, so an invariant closed subset, then the image is closed inside of y. Fourth, if we have now two invariant closed disjoint subsets, then the images do not intersect. They are disjoint as well. And fifth, a little bit upwards. If we have an open subset, then the map that takes regular functions on U to regular functions on pi minus 1 of U is an isomorphism over the ring of invariant functions. Okay? So that's an important property, right? Because you see that this map pi is affine, of course, because we have affine varieties. So if you have an affine open set here, then the inverse image is affine, so that what this is saying is that U is the quotient of pi minus 1 of U by the action of G, right? By applying this exactly same statement, right? Because if you pick pi, then you have the induced map from pi minus 1 of U to U, right? And the ring of functions of U is the ring of invariants. So it's a quotient. So that says that this quotient here is also locally over the base a quotient. If you restrict to an open set, then what you get is, again, a quotient map, which is something that you don't get at all from this categorical definition. So it's a good quotient. So we're going to spend maybe the quotients on.
Is it the structure of a variety or?
Yes, I mean, well, I'm giving a variety. I mean, the structure is given here, right? Right? From this structure here, I get the affine variety, and I'm just simply saying that every open set is also a quotient, in this sense, a quotient of the inverse image. Okay. So it satisfies this property here. Exactly, yeah. Well, you may do that under certain conditions. That's not what we're going to do later. So we're going to first prove this. This is the affine case, and then we're going to jump to the projective case. Okay? And then it's going to be some gluing. You're going to see it. Okay. Yeah? Oh, yes. No, you don't need that. Of course, I mean, for closed. So closed. Yeah, I think it does, actually. At least for reductive groups. Yeah. Or No, I'm not so sure now. Maybe you need characteristic 0 for that. And think of linearly reductive groups. So you're saying that if I pick a closed subvariety here, right? If this u would be a quotient of pi minus 1 of u. I'm not sure. I think you need a characteristic 0 for that, or linearly reductive. Not so sure. Huh? Reductive, yeah. For this statement, it's just reductive. Yeah. Even though, as I've done before, I'm going to assume linearly reductive in the proof. But the statement is valid. You can find this in the book by Newstead, for instance. Okay, so let's prove this. I'm actually going to prove everything here below and leave I for basically the end, except that I'm going to prove that the map collapses orbits, that sends orbits to points. That's simple. So given x in x and g in g, right? And any regular function on y. So remember that this is kx of g. Mm-hmm. Then if I pick f and evaluate it at the image of this point, mm-hmm. So what do I get? So this is composition by pi, right? But the composition by pi is just the inclusion. Right? So this is the same thing as this. If I view the inclusion here, just f inside here, right? But f is invariant, it's in here. So that's the same thing as f of x. And again, this is f of pi of x. Okay. Right? So the composition, remember, is the inclusion. We're going to use it sometimes. And then, I mean, the evaluation by f is the same, whether on this or on this, right? But y is affine. So if the functions are equal, then the points are equal. For every x in x and g in g. Okay, so it collapses orbits. Okay. Now I need to show more here, but I will leave this to the end. Let's show 2. So we need to show that pi is surjective. So let's pick a point. And let I be the ideal of this point. So the maximum ideal corresponding to this point. And then an exercise, which is to show that, remember, K of y is the ring of invariance. So I have an ideal here. I can extend it to kx and come back to the ring of invariance, and then I get back I. You remember that we did this before for a linear action of G on an affine space. Right? You can use actually the same proof, or then you can use the embedding of X on AN and some sort of argument, but actually the same proof works. Right? So I'm leaving this as an exercise, but here you need linear reductive. So I'm going to start assuming that. But if this is the case, right, then I of kx must be different from the kx. Because otherwise, when we intersect, we get the full ring. And that's not the case. Right? So it means that we have an ideal, which is contained in a maximum ideal. This maximum ideal corresponds to a point. And this point must give me y back. Okay? So this is the surjectivity, which already uses, as I mentioned, properties of the group. So we're not dealing with just any group here. Okay, so let me show now 5. Notice that since we have proved that pi collapses the orbits, we have that this pi minus 1 of u is G invariant. Right? If x is in there, G of x is in there as well. Now, every open subset of Y is covered by principal open sets. And if you show this for a covering, then you get it for U. That's easy to see. Okay? So it's enough to show 5 for a basis of the topology. Why? So, for principal open sets. Okay? So it's just a gluing argument, simple. So we're going to consider then U as Y of F, the points where F is non-zero, where this F is a regular function. Okay? Then the inverse image of U is X F composed with pi, right? And if we view, I mean, this is just the inclusion, right? So that's, if you want, X of F. Okay? So F is an invariant function on X, so it's a function on X, and the inverse image is this principal open set. And now what we have to show is the following. So since the map is surjective, this is injective. And of course it factors through here, right? Because of this. Right? And so what we have to show is just that it surjects onto this. So I'm going to pick an invariant function here and show that it comes from a function on U. So let H be an invariant function. Right? And what I want to show is that it comes from a function on YF under the map pi. Well, since it's a principal open set, right, there is an integer n such that Fn times H extends to a function, the global function next. Right. Now, F is invariant, right? Because it's on Y, so it's an invariant function. And H is invariant as well by here, but of course on X of F. So that means that Q restricted to X of F is invariant. Now, it's possible to do it slightly different, but I will be lazy here. The multiplication F times Q is invariant. Right? Because it's 0 where F is 0, and where F is non-zero, it's invariant. Right? Of course, if you're dealing with non-reduced, and I'm not dealing with that anyway here, you have to be a bit more careful here. But that's enough. And so that means that this FQ belongs to Kx of G, right? And you see that F n minus 1 H extends to this FQ, right? And so, what? Here. Right, so of course then since we're in the ring of invariance, this FQ factors through Y, right? This here, fn minus 1, also factors through y. And then you see that h factors through y. Right? It's just the function, the quotient function, restricted to yf, where f is non-zero. Okay? So it was just a matter of seeing that we could have a Q that was invariant. Right? So we can extend, but actually by an invariant function. Okay, so that takes care of 5. Now let's show 4. And to show that, I'm going to use a proposition. In fact, it's going to be a direct consequence of that. So let G be a reductive group acting on an affine variety, X, so as in the statement of the theorem. And if Z1 and Z2 are non-empty, invariant, closed, disjoint subsets of X, then there is an invariant function G such that f of Z1 is 1 and f of Z2 is 0. Okay? So except for this G on top, this is trivial because Z and 1, Z2 are disjoint. But what I'm claiming is that if they are invariant, then you can get an invariant function that does this separation. And if you prove that, then we're done, right? Because that function descends from a function on y, and that function sends pi of z1 to 1 and pi of z2 to 0. So they cannot intersect. So let's show the proposition then. Let's put here what we have already proved. So I prime, double I, 5, and now we're proving 4. Okay. So that proposition, proof of proposition. So let I be the ideal of Z2, yes, inside of K of X. Okay. So the ideal of Z2. We have a map, a composite map, to the quotient. So that here is the ideal of Z1. Okay. So the same notation. And then this composition is surjective. Because the sum of the two ideals must be the unit ideal, since they are disjoint. Okay. And so let me call this phi. So here I have 1, or 1 bar if you prefer. So the identity, so the function equals to 1. Right. And so since this is surjective, there is an f in I such that phi of f is 1. Okay. And then this follows the same patterns of proofs. I mean, this f is a function that is 1 on Z1 and 0 on Z2. It's not necessarily invariant. So what we're going to do is try to find an invariant function inside the space generated by all translates of f, as before. So indeed, it's the same thing. We pick V the space generated by this, right? And we have that phi of v is simply all the fg, go to 1, right? Because, I'm sorry. G. So what yeah, well, exactly, because 1 is invariant. Anyway, so this goes to 1. Okay. So again, we have this linear functional taking this finite dimensional space, which is invariant. So V is inside I. It's inside I because Z2 is invariant. So a function that is 0 on Z2, their translates are 0 as well. Okay, this is invariant. And then assume G is linearly reductive. And then we get that there is an H in V such that phi of H is 1 bar. An H in V invariant such that phi of H is 1 bar. Right? It's that same statement again. Okay, and then that's done because this H belongs to V, so it belongs to I. So it's 0 on Z2. And when we restrict to Z1, it's 1. Okay. So that gives us 4. Now let's prove 3. And then 1, the rest of 1. Okay, so to show 3, so we have something which is invariant. And we may assume that it's non-empty. We want to show that the image is closed. If the image is Y, then okay. Okay. So suppose it's not. Let's pick an element then, any element in the complement. And what I want to show is that there is an open neighborhood of this point inside the complement. Okay? So that would be enough. Now, since pi is surjective, we have that the inverse image is non-empty. It's, of course, closed and invariant. In X. Right? Invariant because the map collapses orbits. So, and of course, the inverse image is outside outside Z. So we have the case where this intersection is empty. Okay. So that means then that there is a function. So I'm not going to use, well, I could use it, but anyway, I'm going to use the proposition. So there is an invariant function such that f of z is 0 and f is 1. Okay. So this function is actually a function y, because it's invariant. So f is a function of y. And we have that f of y is 1, and f of pi of z is 0. And that means that y belongs to the principal open subset, yf, and everything on this principal open subset is in the complement. Because f is 0 in pi of z. Okay, so that's the proof. Right, so that essentially shows that this is open, and then that pi of z is closed. Okay, now we have to show complete the proof of 1, the first statement. Right. So now we have to pick any morphism that collapses orbits and show that is induced from a map from Y. So let me pick psi, any morphism, such that psi of gx is equal to psi of x for every g in g and x in x. Okay? So we define phi from y to z as follows. I pick y and I take it to psi of x for x in x such that pi of x is y. Okay? So I know that the map pi is surjective, so I know that such an x exists, and I take the value of psi on that point. So I get a function. Okay. What I have to show, of course, I mean, by the very definition of this function, I have that phi composes pi is psi. And there is no other way to define phi because pi is surjective. So phi is unique. So what I have to show is that this is a morphism. That is well defined because there is a choice there. And a morphism. Okay? Okay, first of all, to show that it's well defined. So, for that, we use the claim, which says that, okay, if at two different points give me the same image, then, and actually if and only if, their orbits, their closures intersect. So let me put the notation here. We're going to use this more frequently later. This is what I've been calling the orbit. O of x is the orbit of x under the action. Okay. So that's the claim. And from the claim, right, so what we have to show is that if the x1 and x2 have the same image, then psi of x1 is equal to psi of x2. But psi collapses orbits, so it means that psi of x1 is the same thing of psi of every point in the orbit, and so in the closure, because it's continuous. And since they have a point in common, and the values are the same, so this is equal to this, and this is psi of x2. Okay? So this is because they have a point in common, so the values must be the same. And the claim is easy to see, so proof of claim. First of all, again, the same thing. If the orbits have a point in common, if their closures have a point in common, then I apply the same reasoning to pi here. And then I have that pi of x1 is equal to pi of x2. The same reasoning. Pi has the same property as psi. Right? And for this part here, so let me consider the reverse statement. So if this is empty, right, then that's 4 here, right? We have invariant, we have so they are invariant, the orbits are invariant, and so their closures are, and they are disjoint. So the images must be disjoint. Okay, but their images are just points. The point x1, pi of x1, and then the point pi of x2. Okay? Right, now that it's well defined, let me show that it's a morphism. I'll first show that it's continuous, that we have a continuous function. So that so phi is continuous. Okay. So let W be something open here. And I want to show that the inverse image is open. Of course, the inverse image by psi is open. But psi is the composition of these two functions. So that's pi inverse of phi inverse of v. Right? And since pi is surjective, what we have is that pi of v is the inverse image of v. Okay? So we have to show that pi of v is open. That's that. Now v is an inverse image, right? So that pi of v is simply pi of x, or that is y, minus pi of x minus v. Right? Because v is an inverse image. Right? And x minus v is invariant. Is a closed invariant subset of x. Right? Because v is open, and it's an inverse image by psi. Right? That collapses orbits. So then we use 3 to say that this is closed. And then pi of v is open. Okay? So it's continuous. And now, to show that it's a morphism, we're going to show that by composition, it takes regular functions to regular functions. That's enough. Okay? So suppose now that that W that I put there is open, and besides open, it's affine. And let's consider a regular function there. Then we know that f composed with psi is invariant. It's invariant again because psi collapses orbits. So it has the same values on X or on any translate. Okay. Of course, I mean, we've just seen that this is V, which is pi inverse of pi of V. So we're dealing with an invariant function, right, on the inverse image of an open set. Then we use phi. So we use phi. What else? We use 5. Use V. Yeah? Since f of psi is in here, so pi of V is just phi inverse of V. So, and it's invariant. So there is a function, I'm calling this H, such that f psi is equal to h pi. Okay, and this is induced by pi. Right? But then psi is the composition, and pi is surjective. So this pi is surjective. And then it's over. Right? So the composition takes regular functions to regular functions. Okay? So that's the proof. Okay, so you see that we get a quotient with very nice properties. This claim here characterizes the points that we have, right? So we're parameterizing not really orbits there, but sort of closures of orbits. So even though this is a quotient, it's not necessarily what we would call an orbit space. Okay? That is, the fibers of pi are not exactly necessarily fibers, are not as necessarily orbits, right? But they're closures. So let me make a definition. So let G be an algebraic group acting on a variety X. Then, that's a terminology that was introduced by Mumford. We say that an affine map pi. So let me emphasize here affine. Right? We say that an affine map is a good quotient if these 5 properties are verified. So a good quotient is an affine map, which is a quotient, but has all these properties here. Right? Send closed invariant to closed, disjoint to disjoint, and has this local property here. And we're going to say that the quotient is geometric. If, in addition, the fibers are orbits. Okay? So as I said, I mean, it could be more than an orbit that you're collapsing, but we say that it's geometric, if that's the case. And in this case, Y is an orbital space. You can take that as a definition, but it's clearly in bijection with the set of orbits, and it has a structure of a variety. Okay, yes? The orbits are closed, yeah, because they are inverse image of closed points. Yeah. Oh, you mean that it's equivalent? Yes, it's equivalent. That the orbits are closed. Yeah. Because of that claim that I put there. Okay, so then, I mean, if you have a reductive group acting on an affine variety, you have a good quotient. In fact, you don't need to check everything there. Let me put a lemma here. Yes?
If you add the group out
Properly. What we need is that the orbits are closed. So here, in a sense, yeah. I mean, you still need all these conditions, right? To have a good quotient, and then just the fact that the orbits are closed, you get that. Right. Yeah. Oh, you can do that. In fact, I mean, we don't want to leave this abstract here. We're going to see conditions where the quotient is geometric, and that's exactly when the orbits are closed. Okay. So lemma. So let the G be a reductive group acting on a variety X. And let's consider a map, a morphism. Then pi is a good quotient. If and only if the following conditions are verified. Only the following conditions are verified. So first, pi is affine. Second, part of 1 there is pi sends orbits to points. And third, condition 5, but as I mentioned there, I mean, it's just for a basis. So there is a basis of affine open subsets for the topology of Y such that for every Y in this basis, the induced map is an isomorphism over the invariance. Okay. So you don't need to check those intermediate conditions. They come for free. And the proof is simply to observe that if we look at, if we pick then an open set in the basis, then the inverse image is invariant by 2 and affine by 1. Okay? And the map is a quotient map, is a good quotient by the theorem. Theorem 5. Right? Because what this is saying, and by 3, of course, by theorem 5 and 3. So what this is saying is that the ring of U is the ring of invariance. Right? And for a reductive group acting on an affine variety, that's the good quotient. Okay? So now if you have a good quotient, you have all these properties here. Right? And then, I mean, if that is surjective, then the whole pi is surjective. Then you can prove all these statements here by using the fact that they are locally true. Okay? So we have that 1 to 5 hold for this guy here, and then they hold for pi. Okay, so so 2, 3, and 4 are actually very simple. 5 is given. Right? 1 is you have to reason just as I reasoned here. So it's the same reasoning using the already proved properties, 2, 3, and 5 for the map pi. Notice that basically this is telling you the local property of being a good quotient, right? Because if all these properties here, when you restrict to any open subset of Y, they're still going to hold, right? So if you have a good quotient, then over any open set, you have a good quotient. And conversely, if you have a covering of Y such that when you look at the inverse images, you have a good quotients, then you have that the map is affine, you have this, and you have this. Right? Because you can consider a basis of open sets containing in the open sets of your covering. Right? So it's a local property. So the corollary is that in this case, right, a reductive group acting, the corollary is that pi is a good quotient if and only if there is a covering U of Uy such that pi restricted to pi inverse Ui to Ui is a good quotient. Okay? So it's local on the base. All right. Now we're going to move to the projective case. And we're going to use a patching argument, a dilemma. So I have to erase this, or let me leave this here. So we go to the projective case. So let's try to globalize it. And the thing is that, in principle, we can't work in the way that we did for affine varieties. So if you had an affine variety, right? And a group acting, an algebraic group, on X. Right? So what we showed is that you can lift this action to a linear action on an affine space. So G lifts to a linear action, so action by linear transformations on AM for some embedding. X into AM. Okay. Now this is not true anymore for projective varieties. So what we do is, and luckily it happens in a number of cases. There are conditions for it to happen also, but it happens automatically in a number of cases. What we do is we sort of require that something happens. Something like this happens for projective varieties. So definition, let G be an algebraic group acting on a projective variety, X. Then linearization of the action consists of an embedding x iota of x into Pn and a linear representation rho of G into GLN of n plus 1, right? So it gives you an action projective space such that the induced action on Pn, given by this representation, restricts to the action on X. So what we had before as a result, as a proposition, now we have as a definition. Right? And what I'm saying here in terms of diagrams, so we have an action of G into Pn. Right? So if I call, let me call bar the map from the affine space to Pn, right? And then what I have here, this map is simply I act on X, it's GLN plus 1, and then I take the bar. So this is the action induced by rho. Maybe it's better to use rho here. I act on X, and I put the bar. Right, so that's the action, and what I require is that, so that's 1 times iota, that's iota, and what I require is that this action here lifts this action. See? Okay. In general, a linearization is actually an action on a line bundle over X. Right? And then you have to fill the blackboard with diagrams to explain that. But what happens is that in a lot of situations, the existence of this action imply that the line bundle is ample. Right? And if you have an ample line bundle, a power of it is very ample, you can show that the linearization acts on this power, and basically what you get is this. Okay? Conversely, if you have this, you have an action on the line bundle O of 1 restrict to X. Okay? So this is just to say, because the terminology here is a bit different from that on Mumford, I'm using actually the simplification by Newstead here. Yes? GLN. GLN plus 1. Exactly. So, yeah, so what you have is a map, right, from GLN plus 1 to PGLN. Huh? No. No converse. What is there is that we're actually going to use this. This is a finite map. So up to a finite map, you have an inverse. Right? We're basically going to use this, but no. Okay. So suppose that we are in this situation then. Suppose that we have a linearization. So suppose that X is inside Pn, and we have this action rho, right? And the induced action leaves X invariant. So that's what you get with linearization. So suppose we are in this situation, right? Then what we can do is the following. We can look at the ideal, the homogeneous ideal defining X. It's invariant, right? Because X is invariant. And so I is invariant. So we have an action of G in the quotient that corresponds to the cone. Right? So the affine variety given by this quotient. Okay? So now that we have an action on a affine variety, we can look at the quotient using the theorem we have already proved. The quotient is has a ring of functions, this, right? And since the action is linear, right? When you act on forms of a certain degree, you get forms of the same degree, right? And so this is a graded K-subalgebra of C of X. And since it's graded, we can consider it proj. So the associated projective variety. Okay. Now, since we have the inclusion here to here, we have a map. At least a rational map. It's a graded, finally generated, so that's important, of course, to get something projective here. Okay? So we can try to do for the cone what we did for the affine variety, and then we get a projective variety, but we get a map that it's not defined everywhere. Right? It's not defined on the whole X, but the map is defined on an open subset. In particular, it's defined on this subset XSS, which is the set of points of X such that there exists a homogeneous. So X is also the set of variables. So a homogeneous polynomial of invariant of positive degree such that f of x is non-zero. Okay? Because, of course, I mean, when we restrict to C of x, this gives me an element in here. And if f is non-zero, that means that the map is defined. Okay? So this SS there stands for semi-stable. And that's the definition we're going to give. So we're not going to get a quotient on, well, if that is a quotient, on all of x, but on an open subset. So definition. Okay. So let the G be an algebraic group acting on X projective. Assume a linearization. Okay, so we are in that setup. And then we say that a point X on X is semi-stable. And then there is this slightly stronger condition is stable. If exactly what is there, there is an invariant polynomial of positive degree such that f is non-zero or such that x is in this principal open subset, x of f, the set of points where f is non-zero. Okay? Of course, I mean, since f is invariant, this is an invariant open subset of x. And for stability, I require that respectively, and so I require this, but also that this f is such that the orbits of the induced action on x of f are closed. Any D. Okay. Equivariance with respect to the linearization. The notion differs. Yeah, it varies. Depends on the linearization. Yeah, it does. Exactly, yeah. So the embedding is given by a very ample line bundle, right? So it depends on the choice of that line bundle and the linearization that is the action on that line bundle. Yeah. No, this definition is certainly dependent on that. In fact, there have been many studies in the past 20 years to try to understand the dependence on the choice of polarization. And that dependence, there is a phenomenon that they call wall crossing. That is, you have a stratum where nothing, I mean, everything is okay. I mean, it doesn't depend, but as soon as you pass to another stratum, you cross a wall, then things change. So that's certainly depends on the polarization, on the linearization. Okay, so we have all this structure there, and we got better to have a result, and we do. Let me just denote XSS, the set of semi-stable points. It's open in X, right? Because every XF is inside there, right? And we have XS, the set of stable points. And that's also open. Right? Because I require that all the orbits on XF are closed. Okay? So all the points of XF have this property here. They are stable, if that holds. So the theorem is, well, the same statement here. So G reductive, acting on something projective, right? Assume a linearization. So that's an embedding into Pn with the corresponding linear transformation. Okay, so assume everything we have there. And then we have constructed from here a map to Y, which is this proj. And then, finally, if we have all this, then this map is a good quotient. And second, if we look at the image of, if I call YS the image of the stable locus, then YS is open. The stable locus is the inverse image of YS. Okay? And the induced map from XS to YS is a geometric quotient. Okay? So for the stable locus, you get a geometric quotient, you get an orbit space. And for the semi-stable locus, just a good quotient, but then you get a compactification of YS. Okay? So you get an orbit space for the stable locus and a compactification of that orbit space. So let's prove this. I'll briefly sketch I. And then we might want to leave this for next lecture. Let's see if I have time. So it's quite simple, actually, I. So I just pick an element. A homogeneous polynomial of degree d, positive degree, which is invariant, right? And then what? Sorry, what did I write here? Right, so since it's invariant, it gives you, when you restrict to Cx, something here. Right, so a homogeneous element in here. So you can consider the principal open subset. Right, so the set of points such that F is non-zero. Right, because that F is in this ring here. And the inverse image is simply XF inside, which lives inside by the definition of the semi-stable locus. Okay? So Y is covered by these principal open subsets, YFs, and as we cover Y, the inverse image of them will be affine and cover XS. So that gives you the map is affine. So if you remember that lemma, we had to prove that the map is affine. We had to prove that it collapses orbits, but that's simple. I'm not going to do it here, but it's easy to show because we pick Y as the ring of invariants. So we have this. So that's 1, that's 2. And then what we had to show for that lemma is that you had a basis for the topology of Y such that you get a quotient over these bases, over the open subsets of these bases. And of course, the YF form a basis. For the topology of Y. Okay. And so it's enough to show that when I look at this XF, right, the inverse image, that the ring of invariants is the ring of YF. Okay? So that's part 3 of that lemma. Once we show that for a basis of the topology, then we have a good quotient. Okay? Or equivalently, right? So since this is open subset, so what we have here is the cone of C, the cone of X, right? So that's the coordinate ring of X. And we localize at F, picking just the quotients of degree 0. And then I look at G. So G acts on this, so it will act on the localization. F is invariant. And then what I have to show is that this is on this side. So the ring of coordinates of Y is the invariant ring. And then I localize at F. So that's what I have to show. Yeah? And that's an exercise from this. Yeah? So it's quite simple, actually. Okay. Now let's see if I can prove 2. But I will leave a proposition out, and I'm going to do the proposition next time. So let's prove 2. This is not difficult. In fact, we have that when we remove from XSS XS, this is closed, invariant, right? Then the image is closed. Once we prove I, we have that is a good quotient, so the image of invariant closed subsets are closed, right? And I set Y prime to be the difference. Okay? So to show that this difference is exactly XS. Oh, sorry. XS is the inverse image of this. Okay. So once we show that, because once we show this, then what you have is that YS, which is the image of XS, is simply Y prime, because the map pi is surjective. Right? So that tells you that YS is open, and it tells you that XS is the inverse image, right? And it tells you that this is a good quotient. Okay? All right, so what we have to show now is this. right? And the fact that it's not just a good quotient, it's a geometric quotient. The fact it's a good quotient, it's because of that local property I told you about. Okay? And the proposition that we're going to use to be proved last time is that for every x in the stable locus, the orbits inside of xs, so the closure inside xs are OX. Okay, so the orbits are closed inside XSS. Okay, once you have this, then you have that it's a geometric quotient, right. And I have to finish 5 minutes before. So exercise, finish the proof using this. Okay, it's quite clear, at least this part here, right? Because the orbits are closed, so that we have a geometric quotient. Okay? Okay, I finished.